So here in this lecture we will deal with this old concept of strain. So we kind of revisit what we think about strain, what it is, and how we can define that. Again, so this is something that you already have seen in previous courses in mechanics of materials or others that related to this. And you use that very intensively, so this is not entirely new concept. So strain is again, so it's our attempt to measure deformation. And then if we start thinking a little bit deeper about what we try to measure, is again then we'll easily conclude that there is no way to define strain in a unique way. So there can be many different definitions. Why is it so? So basically, what we have again, so there are some points that we identify in the undeformed case before the deformation happens, and then we have all this mapping and location of all those points that moved into the deformed configuration. So now we'll look at that point, and we start. So what we start to measure is a change in the relative position of 2 points, say 2 neighboring points, or if we look at a particular point. And then while the moment of the points can be defined, and there is a mapping function that one-to-one maps that, or you can use also the deformation gradient that is derived from that. But then what we want to measure the strain it's basically up to us. And again, this is already a measure of how the geometry change that basically we define. So the mapping is something that is very objective, but then how we measure this relative changes, this is again up to us. So here I'm going to illustrate that on the example, on the one-dimensional example, this notion. And so okay, so that's very simple, right? So we have the standard, let's call it a fiber in one dimension, and the initial length is L0, and so then after the deformation happens, let's say we stretch this fiber to a new length, so now it becomes longer. Okay, so we stretch it, and the new length in the deformed configuration is L, right? And so then the strain, how it was typically defined in previous basic courses, is that you just calculate the difference between the lengths, and then you normalize it, or you divide it by the initial length. And sometimes it's you would call it, you would write it differently, and you would write the delta, that the strain, right? Let's call it an engineering strain, is delta L, the change in the length, divided by the initial length, right? So, and that's exactly what you have here. So this is your delta L, obviously. Now you can also relate it to the write it in this way, so that can be presented as a stretch. Why so? The stretch ratio basically will be this. So right, so that's this is, if you divide L by L0, you will obtain the stretch ratio in that direction. So how much longer your fiber has become after the deformation. And then the second part here, of course, will be when we divide L0 by L0, so that of course produces U1. And so you can define also that engineering stretch. You can relate it to the stretch ratio, to the stretch of that fiber, lambda, and so that will be lambda minus 1. Now this is one straightforward definition of strain. So just take our we measure, so basically very simple, straightforward. So we measure the length, we measure the change, and so we just divide it and say, okay, so we have some measure of strain. That was standard, that was used before. Now, to start thinking a little bit different in that direction, one would ask, okay, that was very simple, very nice for a simple case. So, but what would you do if, for example, this for whatever reason that fiber was deformed in such a way that different regions in this fiber would be deformed differently? Well, maybe the fiber is made some from different components. Maybe a part of the fiber is from steel, the other part of the fiber is from some softer material, and so of course when you deform it, so the steel part of the fiber will not be deformed and the softer part of the fiber will be deformed more. So basically can be many different situations why and when it happens, but the question is, how do we deal with a situation when the deformation in the fiber is not homogeneous? Meaning, how we define or calculate this deformation or strain if different points of this fiber would be deformed differently. So naturally, what you would do in such situation, you would actually use this the basic definition of the strain, but you would define it locally, right, at each point, and then you would integrate. And all right, so that's a very natural approach. Of course, we can do that, and let's see how it works, even for the situation when you have a regional situation when all of the points of this fiber deform exactly the same. But now I'm going just to use this the same approach of integration. So I will just say, okay, I will use this definition of strain locally and just integrate over the length of this fiber, and I hope to get the same result as here, because, well, as an engineering strain, because well, there is no inhomogeneous distribution, every point feels the same, so they all deform the same, and so that's where we started and that's where we ended. So I'm just integrating, maybe I'll get the same result. Now, and let's see what will happen. So, and we'll call that, okay, so that we'll define a new different measure. So we'll have a different name for this measure. So this is engineering, this is something else, we'll give it a name later, very soon. And so basically what we are doing here is that, so this is our dl divided by l, and okay, so to be, and then we integrate from the initial length to the length in the deformed configuration. Basically, yes, we defined that locally, so instead of delta l, we have this infinitesimal element change in dl, right? So it's not a dl like this. So this is our integral approach already here. So dl divided by l, so we normalize it, so that's our measure of strain. And then we integrate and we see how much was accumulated through the whole process of this deformation, of this path of small changes in delta L. Now, as we go from here to here, right? And so then the result of that integration, obviously, so that is 1 over L, so the integral of that will produce as natural logarithm ln L. And now if we substitute the boundaries of integration, so the result will be ln L divided by L0. All right, so this is very strange. All right, so we also can write it, of course, in terms of stretch ratio, because this L divided by L0 will be exactly lambda, will exactly stretch, which you said, so this is the parameter that says how much the how many times, so how much the initial lengths change, right, from going to lambda 0 to L. So we can call it lambda exactly as we did here. And so it appears that we have this new measure. So it looks very different, right? So there is a natural logarithm suddenly appearing here, as opposite in engineering strain when everything was linear and not clear why. Okay, so and hence we have a name for that. It's called logarithmic strain. So, but again, the logic is straightforward. So we just identified small changes in delta L and integrated over the whole path of integration, right? So there is some logic behind it. So now we actually got a different result because of this process. There is a why would that work, or when that will not work, or will produce us similar results? So what we could do here, so we could we actually can consider a situation when the stretch or when the deformation is not very large. So if that was the case, so then they can, okay, so let's do the following. So first of all, I will just call the engineering strain something that you already know, like epsilon, right? For the just, okay, so we could use that, but let's use epsilon here for consideration of this logarithm strain. And so then that logarithmic strain, this ln, so okay, let's write it here. So this ln L divided by L0. Okay, so that that is not we divided by L0, right? So this is basically this formula. So we can now define it as so this. So we can rewrite it a little bit different. So this will be ln, okay, still ln, but then I can split that L into L0 plus delta L, right? So that how much my how much my L changed. So right, so I L is nothing but L0 plus delta L, and so then we can write that if we continue, so that will be ln of 1 plus epsilon. Why I write epsilon here? Because that's exactly delta L divided by L0, so that's how we define the engineering strain, or simply strain in the beginning. And now what I want to do, I want to write our usual Taylor series, the expansion for that. So because I want to see how that will look like if we expand it around 0, around small values of strain. And then let's call this whole argument here ln, for example, x, just because I want to keep it simple. So then the answer here, so if we write it, the first term will be ln point x0 plus, and now we're getting into the first derivative of logarithm, which is 1 over x here, obviously, and so and so we have x minus x0 and the second term, the derivative will produce as minus 1 over x0 square, and so we have a square element here, x minus x0, etc., and square. Okay, and so and then there will be high order terms, so we can continue with that. Now, okay, so after this very quick exercise, we can let's get to what we actually wanted to say here. And so we wanted to write it in terms of epsilon, and so I'm going to write this expansion around the point in terms of x, that will be 0.1, but in terms of epsilon, we are going to write this Taylor series expansion around point x01. And so if that's the case, so if this is 1, so for us, so this will be 0, this term will be 0, and so then we are remaining, so this is 1, this is minus 1 here, so what will remain here is just epsilon, right? So that will be epsilon here. This is 1, so this 1 again, and so there will be again 1 minus 1, and so what will come out of this parenthesis will be epsilon square. And so if we write this all correctly, then we can say that the expansion of ln of 1 plus epsilon will be so we're getting epsilon, so the first term coming from here, minus epsilon square, right? And most likely I forgot here the factor of 2 here as usual, right? So let's correct that, and so then we have a higher order terms of epsilon to third with a different coefficient here, so that will be already a factor of 6, right? 2 multiplied by, and etc. Right? So we can continue that. But what we are saying here, right? So that's if we look a little bit more closely into what we obtained into this engineering strain, so the first term is exactly as engineering strain, so this is logarithmic strain, right? So the first term is exactly as engineering strain. So the second term is a quadratic term. So if the strain is relatively small, so if epsilon is a small number, or if mathematician will write it something like that, right? So or if it's so then we can neglect higher order terms. So then the difference between the logarithmic strain and engineering strain will be really very small. So we basically say that they would produce identical measures of deformation of strain. However, when the strain itself, this delta L over L0 is a large number, so this more accurate, let's call it more accurate measure of strain, the logarithmic strain, will start to produce more and more significant differences with the measure of strain if we just simply use base it on the change on the length on the global level of the whole sample and the one-step deformation. So this is just to illustrate you that okay, so they of course connected. So and this engineering logarithmic strain basically reduced to engineering strain when deformations are small, but it becomes less accurate to use engineering strain if the deformation become larger. So you do need this nonlinear high order turn to more accurately describe the relative changes between the positions of points. So you want to that's what at the end we want to measure with that, with the strain. And so going back with that, again, so this is our choice how we define the strain. So we can define it in different ways, but we just need to remember that if we want to deal with large deformation and be more accurate about it, then we probably want to to keep this high order terms still in play. Otherwise, we'll not capture this what is called sometimes geometrical non-linearities. And hence another measure that I can introduce here, it's called green strain, and basically takes this exactly this high order change in the strain into account. So you see that suddenly we decided not to change the linear, not to calculate the linear change in the length, but rather to calculate the quadratic measure of those. And so we have L square, the here minus L of the L square of the initial length, and divided by 2 L0 square. And note that there is a factor of 2 which is important again for us. So, and as you can see, so also this one we can show that that should reduce to the engineering strains when when the length when the strain itself, the change in the length becomes very small. Okay, so we can also write this in terms of the stretch ratio if you like. So that's very simple. Now, so when we divide L square by L0 square, so that will be lambda square, so divided by 2, and this is just 1 here. So we have half lambda square minus 1. Okay, so this was in one dimension, and of course we would like we eventually would want to generalize it into 3 dimensions, and so that's our next order of business, to basically to write it not as a scalar in 1 dimension, but rather in tensor notation. So in tensor notation, strains measures in that will be applicable for the three-dimensional formulations. And so then for engineering strain, we will define it in the following way. Again, formally here, so here's our basis here of principal strains, and so principal directions, assuming that we do know the principal stretches and principal directions, then it can be defined in this way, right? So this is lambda minus 1, exactly as it was in our one-dimensional case, but now we redefine it into 3 other principal directions that may occur. And if that's the case, so that lambda multiplying m, the tensor product of mi will be nothing but our right stretch tensor u that we defined before, and these guys will produce as the identity tensor then. And so, and then the logarithmic strain, again, something very similar. So that's where our knowledge about the tensor functions will become handy here to introduce it in an effective way. So basically, we are not applying that logarithmic measure on the basis of the vector of this tensor product, but rather only on the scalar function lambda on the stretch, and so, and then the end, so we can write it as just ln u. So the logarithmic strain is the so okay, so we apply it to the our right stretch tensor u. And then green tensor is a quadratic measure, right? So again, so expanding it from the one-dimensional way how we wrote it, right? So that sits exactly here with this whole scalar, and then again, similar manner as we have done just before. So we can look more closely into the what we have here in combination with lambda and this tensor and so which is nothing but the quadratic term of in right stretch tensor u, right? No, well, in the second part is the trivial standard identity tensor that we'll have here. All right, so now we can look more closely into that our new friend, this green strain tensor. And as we keep going, so at certain point we'll just all right. So let's focus on the green tensor and just for simplicity drop this G. We will not use engineering strain very much here in the continuation. So because we learned that well, that doesn't contain the non-linear terms in the changes, right? So that we want to capture. So we could use logarithmic strain, but okay, why? So sometimes logarithm operation is not very convenient for us. It's much simpler for us to look into just quadratic terms directly, right? And so therefore we just choose to work with green strain, and then just drop that G index here, and we'll continue. But we'll mean by that this is already green tensor. Okay, so let's go and redefine. So what is here in that quadratic square of the right stretch tensor, and see what we are getting here, and maybe we will also once again can connect it to the engineering strain in tensorial case as well. All right, so this is our definition, and so we already know that that u square can be related to the right Cauchy green tensor, right? So that's u square. That's how we defined our right stretch tensor. So C, right? And C, the right Cauchy green tensor, we defined it through deformation gradient, so it's just F transpose F, as it was been here. And so now we can substitute that C with F transpose F. And so this is basically still our green strain tensor E, right? So that's all. Now we can dig a little bit deeper into F and recall that well, that's basically just a gradient of y, right? Or it's a gradient of and y is the new position. New position is nothing but the initial position plus displacement, right? And recall that u is the displacement vector, and again we take the derivative, the gradient operator with respect to x. That's why we have the capital G here. So that was our agreement that when we take the derivative with respect to the undeformed position vector, then we will use capital. So that will be with respect to x. But again, so this is nothing but I plus h, and h, this is the displacement gradient, right? So this is well, that's how we defined it back then. Now we're using this writing, right, of f. So now we are going to substitute instead of f this identity plus displacement gradient. So okay. So the first one we need to transpose. Second one is the original one as it was before. Now let's look into what we have here. So when we open these parentheses, so then what we will obtain? We'll obtain the identity tensor. Okay, so let's say just do a little bit of clarifications here. So these two will give us another identity tensor, right, with plus, and then we have this identity tensor here, so that identity will disappear. Now we have nonlinear term h transpose h, so that we will keep, and we will have one h transpose that multiplied the identity and one h that multiplied this identity. So we have h plus h transpose plus the nonlinear term h transpose h. And this identity is gone because this is minus, and these two multiplied identity tensor just with plus. And so we can say now that, all right, so our green strain tensor can be expressed in terms of the velocity gradient or displacement gradients in this in this simple way. So we have h plus H transpose plus H transpose H. Now, okay, so you may ask here why we're doing this, where we're going with that, and in fact, so we probably could have stopped before, but if we now look exactly into what H this displacement gradient is, so we can realize that basically the first term, the first part of this, basically together with this factor half, is exactly the definition of the engineering strain that we already had before. Why it happens? And so why I'm saying so? Okay, so let's just substitute that our definition of the displacement gradient. Okay, so this gradient u, and so to simplify things, I will just at this point we'll just look into the components. So we'll forget about tensors and just will write the indexes of only components. And so if we write it back in our definition like this here, so then in index notation, so that Eij will be okay. Half is still here, so we have U ik, ukj, or in other notation, so it can be written like here. So this is just half Cij minus delta ij. Now, if I look into the results of 242 and write it here, so then you will see that what happens is the following. So we have the first term will be just dui dxj. The second term will be transpose of that, so it will be guj dxi. And then we'll have the third term that is a combination of these two. All right? And so basically that's what we are looking into. And so this is the strain. And as I said, so the first two terms, if you recall, that was exactly how in general you wrote the engineering strain before in the linear elasticity. Also, this is the linear terms. So the Green strain, the difference comes when the nonlinear terms here become significant and we cannot neglect them. So this is the nonlinear term. You can see that we have the derivative, the first derivative, and here we have this first derivative multiplied, right? So this is a quadratic term. So when the changes are small, or effectively when the engineering strain on the measured strain is small, so then this second term can be neglected, and then we're entirely fine with this simplified linear definition of strain. So we'll be okay with that. But once the deformation becomes nonlinear, so this addition becomes more and more important. And so if we want to actually properly deal with large deformation, geometrical nonlinearity, so this term that comes from the exactly from here, right, for the quadratic term, so that definitely we'll need to account for and to carry with us. So that's what basically Green strain adds to our original definition of the strain or engineering strain. So we have this ability to capture the nonlinear term in strain. All right, so that will be all for illustrating of the strain. So again, so the bottom line is that this is up to us how to define it. But if we choose to define this measure of strain, we need to do it smart. So according to our problem, so if we know that there is a large deformations and geometrical nonlinearities, of course, let's take into account the nonlinear terms. All right, so let's move to our new topic, and that will be in next lecture. See you then.